With science operations underway, the James Webb Space Telescope, JWST, newly reveals our universe. This three-panel image shows the view of the Carina Nebula's cosmic cliffs, as seen by Hubble, top, JWST's NIRCam instrument, middle, and JWST's MIRI instrument, bottom. With its first science release upon us, this new era in astronomy has truly arrived. This comes 6+ months after its initial launch. On December 25, 2021, as the solar array deployed 29 minutes after launch, and 4 minutes ahead of schedule, it became clear that NASA's James Webb Space Telescope was operational, receiving power, and well on its way toward its ultimate destination. The launch was an unparalleled success. For reasons necessitated the long wait. The 18 segmented mirrors must unfold, deploy, and form a single surface that's calibrated to a positional precision of 20 nanometers. While the secondary mirror must then focus that light precisely onto the instruments. Any failure here would have been ruinous for the telescope. 1. Deployment. The observatory needed to unfold into its final configuration. During the first month after its launch, JWST's priority was to reach and enter a stable orbit around the L2 Lagrange point. With the Sun, Earth, and Moon always behind it, there's no chance of any of those sources ever obscuring its view. Hubble, however, from low Earth orbit, is prevented from observing its targets for more than 50% of its potential observing time. 2. Orbital insertion. It needed to arrive at its desired destination. All 5 layers of the Sun's shield must be properly deployed and tensioned along their supports. Every clamp must release. Every layer must not snag or catch or rip, everything must work. Once fully deployed, the 5-layer shield provides passive cooling down to temperatures of about 40 K, shown here is the Sun's shield prototype, a 1/3 scale component. 3. Cooling. All of the components needed to reach operating temperature. This 3-panel animation shows the difference between 18 unaligned individual images, those same images after each segment had been better configured. And then the final image where the individual images from all 18 of the JWST's mirrors had been stacked and co-added together. The pattern made by that star, a snowflake unique to JWST, can only slightly be improved upon with better calibration. 4. Calibration and commissioning. Each and every component requires it. This includes both the optical system and each science instrument as well. Although the MIRI, mid-infrared instrument, of the James Webb Space Telescope achieves the lowest resolution owing to the long wavelengths it's sensitive to. It's also the most powerful instrument in many ways, capable of revealing the most distant features in the universe of all. The original, first light, image taken with MIRI, the mid-infrared instrument, were taken on April 13, 2022. With the science goals of achieving better than 1 arcsec pointing resolution and to determine the geometric distortion and scale of MIRI's imaging and spectroscopy capabilities. Where the 7700nm and 5600nm fields overlap, MIRI's first color image could be constructed. Arguably, the most difficult instrument to commission is MIRI, the mid-infrared instrument. This 6-panel view of various images taken with the MIRI instrument, during commissioning, represents some of the fields that were viewed in order to identify and mitigate many of the technical issues involved with the instrument before science operations began. The rightmost image in the top row is the composite of the 7700nm and 5600nm filters from MIRI's first light image. Unlike all others, passive cooling to 40 K is insufficient for MIRI. The MIRI imager filter wheel includes 10 filters for imaging, a 4-filter diaphragm, combinations for coronagraphy, 1 neutral density filter, 1 ZNSGE double prism for the LRS mode, 1 opaque position for darks, and 1 lens for ground testing purposes. These sets of filters enable us to view the mid-infrared portion of the spectrum as never before, but only at sufficiently low temperatures. Probing the longest wavelengths, from 5 to 30 microns, demands operations below 7 K. The cryo-cooler for the mid-infrared instrument, MIRI, as it was tested and inspected back in 2016. This cooler is essential for keeping the MIRI instrument at about 7 K, the coldest part of the James Webb Space Telescope. If it gets warmer, the longest wavelengths will return nothing but noise, as the telescope will actually see itself radiating at higher temperatures. JWST is pioneering a unique, closed-system cooler. What appears as a relatively empty field was designed to study the variation in the sky background as a function of telescope pointing and across different wavelengths. This helped identify what the differences were from previously being at a hot to a cold position caused within the detector. A spiral galaxy clearly rich in polycyclic aromatic hydrocarbons pops out in green. It'll keep Miri cryogenically cold indefinitely. This commissioning image shows a dust-rich region just a few degrees offset from the true galactic center. Scientifically, the green colors indicate the presence of organic molecules, polycyclic aromatic hydrocarbons. The data was used for measuring the level of stray light in the detectors. More than was anticipated was found in the Miri data, particularly from 5 to 10 nanometers. Miri's arsenic-doped silicon detectors encountered some novel issues. This shows Hubble's, left, and JWST's Miri instruments, right, view of the same object, galaxy NGC 6552. With an active center, the Miri plus sign spike pattern clearly emerges. However, one unfortunate feature of Miri is that when the detector becomes saturated with a too bright source, an afterimage can persist for up to 25 minutes. This image was vital for helping identify what Miri needed to do to recover from such exposures. These detectors saturate when viewing too bright sources, producing afterimages. This view shows the famous Cat's Eye Nebula, as seen by Hubble, L, and JWST's Miri instrument, R. Knowing how a saturated detector produces unwanted afterimages, it then becomes important to learn how to remove such saturation and mitigate it across the Miri detector. Observing the Cat's Eye Nebula allowed the Miri team to identify precisely how to do that across all three of Miri's detectors. The fix is thermal cycling. Warming the instrument to 20 K and cooling it back down. This remarkable image was a bonus freebie, taken in parallel mode while the NIRIS instrument was being used to observe a small nebula in the Large Magellanic Cloud. In Miri's field of view just happened to be an asymptotic giant branch, AGB, star in the process of losing mass. The characteristic plus sign in its spikes, much brighter than the standard hexagonal spikes, can clearly be seen. Miri spikes aren't hexagonal, but display a unique plus shape. Inside the arsenic-doped silicon detectors in Miri, reflections were intended to be minimized. However, at the shortest, 5 to 10 micron, Miri wavelengths, up to 73% of the light might be reflected internally, represented by the downward arrows at various interfaces, creating an enhanced plus sign atop of JWST's standard point spread function for its light. Internal, short wavelength reflections are the culprit, software is the remedy. This image showcases the same region of sky in the Large Magellanic Cloud, all without a source bright enough to saturate the Miri detector, in each of 9 separate filters. The instrumental aim was to generate sky flat field images, which are necessary to understand and achieve high values for the signal-to-noise ratios that will show up. Miri's wavelength capabilities cover 9 independent mid-infrared ranges. This 10-frame animation shows each individual filter used to view the same region of the Large Magellanic Cloud, LMC, with an assigned color RGB composite used to bring out various features available to Miri's unique view. Now fully commissioned, Miri is revealing the mid-infrared cosmos. This view showcases the difference between the JWST's NIRCam and Miri views, with NIRCams being far sharper and revealing more objects. The Miri view reveals dusty details that no other wavelength can, however, including the abundance and composition of dust inside, which relates to a galaxy's star-forming and life-forming potentials. In the Miri view, red equals gas-rich, blue equals gas-poor, but still present, green equals organic molecules, especially polycyclic aromatic hydrocarbons. Mostly Mute Monday tells an astronomical story in images, visuals, and no more than 200 words. Talk less, smile more.
That was it for now. For more content like this, subscribe to our channel.